7, day 2. We're continuing to get into sampling distributions. Oops. We'll start by discussing what we'll call an unbiased estimator. If its mean of its sampling distribution is equal to the true parameter being estimated. Down below you can see unbiased doesn't mean perfect. It means that it's kind of in the ballpark of what it's measuring. Okay. If it's unbiased, your sampling distribution will be centered on the parameter. That's the best terms to put it in. Okay, you're still going to have variability. The bigger the sample, the less variability we'll have, but we'll always have some. But if it's unbiased and if it's good, right, we'll be centered over that parameter, and the samples that we get where we have an estimate that's a little too high should be about the same as the samples that are a little too low. Remember, bias comes into play when we're consistently off on one side or the other. This is an activity for in class. We're going to do two things. We're going to get data on every student I have, stats and otherwise, to get how much sleep they typically get in a night. We're going to build a population distribution, and then we'll build a sampling distribution. Okay, essentially what's going to happen is we'll put together sample size 4. Okay, this is going to involve a mean, but it's going to be kind of our first attempt at really diving into not just that sampling size is related to variability, but how. Because that's a place that we want to go in Chapter 7 with sampling distributions. Very specifically, like getting to a point where we have a formula that tells us here's how they're related. Alright, this is just getting at that same idea of sample size goes up, variability goes down. We have population data here that adult males are normally distributed with a height of 70 inches and a standard deviation of 3. Okay, we have two sampling distributions, or approximate, because each one has 1,000 random samples. The sample size here is 100. Okay, would you call this sampling distribution unbiased? Think back to that first slide. I would say yes, because right here we know the parameter is 70, and that sampling distribution looks centered right at 70. So we're getting samples that are right over where we want them. About the smallest we got was down to 69. About the biggest was up to 71. Okay, so it only has a range of about 2 inches, because 100 is a pretty decent sample size for measuring a mean. Okay, now look over here. This is what things would look like with a sample size of 1,500. That's a really large sample. Okay, again, right over 70. Look how little variation it has. It looks like 69.8 to 70.2. you take an average from 1,500 and you're getting an estimate that's really, really close to 70. Okay? We'll kind of generalize it on the next slide here, but sample size goes up, variability goes down. Okay, so this is where we get a little bit more serious about this, to get into variability. Eventually we're going to get some formulas for standard deviation. We're not going to get them in 7.1. We won't get them until 7.2 and 7.3. But if we want to use those standard deviation formulas, we have to stick to the 10% condition. Okay? As soon as you pass that, all of a sudden it's like you're creeping towards data for the population and not the sample. So we have to stay within that 10% rule. Okay? An important note there, and this is just formalizing what we've talked about variability. If you take a bigger sample, your variability goes down. We saw that on the previous slide with the heights. Larger samples give smaller spread. They don't eliminate bias. Okay? Those are two different things. Remember, bias is consistently too high or too low. You're not centered where you should be. Okay? But if we were to say here that n is sample size, and sigma is the standard deviation of your sampling distribution. You'll see us talk about this again and again and again. That's a great way to think about it. As n goes up, right? That's the equivalent of taking a bigger sample. Sigma goes down. Okay, that's just the general idea. We'll get into the specifics of means and proportions as to how they're related, because they're different for those two measurements, but that's a big idea that you want to be really familiar with. N goes up, sigma goes down. Okay, and again, that's talking about how much spread our sampling distribution has, right? N affects spread, bias affects center. So here on the left we have the population distribution for the amount of time in between interruptions at Old Faithful. The right is the beginnings of a sampling distribution of sample size 10. So here's the kind of things that we could look at if we were to compare the two. We have population data. It's measuring a median, which we typically don't do, but that's fine. Is the sample, median, an unbiased estimator? Okay. Technically, we would say no, right? If it is, it should be centered right around 75, because that's the population median. But there's 75 minutes in between. Ours is 73.5, so it's off. Okay, when we're looking at the center of our sampling distribution, if it doesn't match the parameter, we'd say that there's bias. We're not centered around the measurement that we want to be. And the sampling distribution on the right isn't centered at 75 technically. If we use sample size 20, right, the spread would decrease. Okay, so whether it was the range or sigma, we typically are interested in sigma. That would come down if n was 20. Okay, n goes up, sigma goes down. Then if we wanted to talk about shape of our sampling distribution, it looks to be skewed to the left. So when our samples are giving us underestimates, those are farther off the center than when we're getting overestimates. Okay? The underestimates are farther off. All right, so here's a little analogy to continue the discussion of bias and variability. Okay? So before we dive into those, this works with thinking of a distribution as well. If you are talking about bias, remember we had said the center is off, right? Our sampling distribution isn't centered around where we're supposed to be. In the dartboard analogy, you can think of that as we're missing the bullseye. It has nothing to do with how spread out the shots are, right? Each in the dartboard analogy we're using here, each time we're throwing the dart, we're taking a sample, right? And we're hoping our sample is somewhere close to what we're measuring, which we're saying is the center. You can see two of them, A and C, both show bias. Because those darts that we're throwing are nowhere close to the center. If we are getting into the topic of variability, that just means our spread is large. As you can see in part B, the shots can be spread out, but they're in the ballpark of the bullseye, right? Meaning that right here, this is what we're aiming for. Okay, that has variability, but I would not say it has bias. Okay. D, it describes it as the ideal. Low variability, low bias. So we would need a large sample size to get low variability, but the way we're taking our sample, we'd have to make sure that we're around the bullseye. Okay? C is really bad, high variability, high bias. And A is bad too, that we have bias. Not a lot of variability, but we're still not even close to what we're measuring. Okay? Variability is a much easier issue to deal with. Take a bigger sample. Sometimes that's easier said than done, but if you really want to decrease variability, that is really the one and only way to do it. Okay? Bias, well, we talked about that in chapter 4. That could come from a variety of sources. If it was a survey, how did you word your questions? Did you deal with people lying on surveys? Did you not get responses from people? Did you take volunteers? Okay? None of those have to do with sample size, right? So there's a total different deal that you have to get into if you have bias, but this is a good analogy to visualize the difference.